This is the second video in the probability section. It's about probability trees. Now you will have probably done probability trees before, so this is a little bit by the way of revision. But there is one or two things that I just want to first of all use probability trees in order to kind of describe probabilities. That gives a bit of a hint as to what's going to come later. And the other thing is perhaps a bit of discipline in the way that the trees are presented, because there is a bit of inconsistency in the way that people tend to do them. And I think there's one or two good practices which will help you do these kind of problems. So let's just go straight in to this one. Let's have a look at the problem first. A company assembles drills using components from two sources. Goodbye supplies 85% of the components and Amart supplies the rest. It is known that the 3% of the components supplied by Goodbye are faulty and 6% of those supplied by Amart are faulty. It kind of implies some kind of production process whereby they're getting sort of, I'm not sure it's drills, I think it might be drill bits supplied, and thing that goes into your drill, and then there's some process, maybe just get sharpened up or something like that. But if they could be faulty coming from the supplier Goodbye and Amart, and if they are, even when they've been sharpened up, they're still faulty. So there's some kind of process like that. Okay, so yeah, Goodbye supplies 85%, Amart the rest. It's known that 3% are from Goodbye are faulty and 6% supplied by Amart are faulty. Represent this information on a tree diagram. So we've got the tree diagram here. So we have branches, nodes, and leaves. This is a node. So a branch emanates from a node. We come to another node here, and another branch, and then we have the leaf here, which is the result, if you like, of what we're doing. Now the actual sort of annotation of the event is something that should go with the branch. Seeing it represented, it's on the node, and it doesn't kind of work quite so well. Really, it should go with the branch. And here we've got probability of Goodbye is 0.85. You could just put G, and 0.85 would be acceptable. So if we look at this, is the first level of branch, and this here is the second level. Okay, so in the first case, so what we're saying actually is that when the completed sharpened drill comes out of the end of the factory, this company, if we select one of these things at random as it comes out, what is the probability that it's going to be faulty, or that it will have been sourced from Goodbye, or some combination of that? So we're picking one out at random, and we want to understand the probabilities. Okay, so at this first level of the tree, then we've got Goodbye 85%. So this is this 0.85, and then the Amart, or the rest, which is 0.15. So these two add up to 1. So in other words, all of the branches from a node will add up to a probability of 1. Now, having got to this node here, we're then looking at two different sub-possibilities, if you like. One is the probability that it's faulty, and the second one is that it passes the quality test, if you like. That's the Q. Now, the annotation that I suggest here is that we apply the conditional probability annotation. So this vertical line basically means given that it's a conditional probability nomenclature, which we'll come to later. But I think if you get into the way of thinking about this, then I think it will help. So the point here is, of course, that this probability, this faulty here, is 0.03. This faulty from AMART is 0.06. So the probability of it being faulty is dependent on whether it's goodbye or AMART. However, given that it's goodbye, then the probability of it being faulty or quality is actually independent. So this event and this event, as are this event and this event, are therefore independent. And I think it just helps to clarify also that, you know, this is a different probability to this. Okay, so just sort of keep with that thought. Yes, probability of goodbye, and then the probability that it's faulty given that it's goodbye, or the probability that it's a quality item given that it's from goodbye. These again, these are two branches emanating from the same node here. These add up to 1. Right, so what we've got now is, in the way of probability trees, is we multiply across because these are independent events. And if we multiply them across, then we get the probability of the intersection of these two. In other words, it's goodbye and it's faulty. And okay, so we can just multiply that 0.85 by that 0.03 and we get this 0.0255. So that's what that is. Okay, so, and we can just repeat the process here, goodbye, and then this is 0.97. So the probability of goodbye and it's a quality approved item, 0.8245, and then the same with AMART. We get this probability, and then the probability that it's AMART and it's a quality item is this. So these are the 4 possibilities. Now these are mutually exclusive, so it can't be that and any of the others. These outcomes are completely separate. So we can add these because these are mutually exclusive. So in the way of probability trees, we multiply across and we add going down, and if we add these, we get a total of 1. So we've done the multiplications correctly, and that is our probability tree. So just probability of G, just point this out, the probability of G times the probability of F given G is equal to the probability of G intersection F. Now that gives us a little formula which we're going to use later. All right, so just hold that thought. An assembled drill is selected at random. Find the probability. Find the probability that it is not faulty. Okay, so having got all our leaves calculated out here, what we can do is we can go down all these leaves and find the ones that meet the criteria in B. So we're not faulty. So this one, got a Q there, and that one's got a Q. So those are the 2 of interest. So if you just pull that number across there and there, add those 2 together, we get this probability 96.9655. So that basically is the probability that it is not faulty, which is good. It's a quite high number. Little question here again. This is kind of looking forward really to some other things that we're going to be doing. How do we decide which branches to start with? I mean, we've gone for the supplier there and the quality at the second branch. Could we have done it the other way around? Well, in theory, you could, but the data you're given, this 85 and 3%, really forces you into doing it this way around. And then that's normally going to be the case, but we'll find later actually that sometimes it's useful to be able to construct the tree the other way around, because that gives you some other useful results, and we'll get to that. So this is all constructed with decimals. The only other thing I wanted to mention was, if we just go down here, very often the probabilities are given as fractions, and so I would just say, as another, this is from another example, but if if they're given in fractions, when you multiply across, don't be tempted to simplify that. 3/15, for instance, you might be tempted to write it as 1/5. Would be quite natural to do that, but it's more useful actually if you keep it in that raw form, because as we will want to add these, including when we want to just check that it adds up to 1, then it's much easier if they're all in 15ths, and you can see that the total at the bottom is 15 15ths, which is 1. So that would be a little tip I would suggest. Okay, so that is all we need to say, I think, at this stage about probability trees. We will come back to these, but I think that's all we need to do at the moment. So hopefully that's as useful. And therefore, I will see you in the next video.